This video is from my earlier course, back when I was building out these ideas. The fundamentals I cover here are still solid, but the frameworks have evolved significantly since then. Head to systemthinkinglab.ai to see how this turned into a full course series. Hello, and welcome to the next lesson, Introducing the Seven. Learn about the essential building blocks. Let's get started. So in this lesson, we will introduce seven, yes, just seven building blocks for which we will create system designs for 15 real applications. In this lesson, we will show you their trade-offs, their strengths, and weaknesses to provide you the base intuition to guide you through these case studies. We will also introduce three additional and external entities representing critical and necessary external forces that applications must deal with. We'll talk about more about that in a little bit. But one thing I want to just note is that we've been building in this section, we've been building a lot about these building blocks and what can they do. We talked about task and storage units and how these are like the fundamental units that you'll see in everything, the zeros and ones that go into stuff. Now, what this building block method is that we're identifying seven entities, right, that consist of these task and storage units. And just by rearranging and using combinations of these things, we're going to build 15 real applications, basically design 15 real applications. And we're hoping, what the goal of you to see is that how similar different systems can be, how different systems can be, but the fact that you can really just move these seven building blocks around to make different applications is very powerful. And so this lesson's about really fully understanding what each of these building blocks are, because once you do that, then you can, when you use them into all these different applications, you'll fully, even though it's a high level design, you'll be able to fully understand how a system is working, essentially. So let's get to it here. I'm going to list them right here. So right now we have the seven building blocks here. So on the left hand, I have this concept of type. So we have 2 task building blocks and 5 storage building blocks. Now, this doesn't mean that the task type of a building block has nothing but task units, and it's the same for storage. What it means is that the primary use for it, the primary reason or why we use it, is to either, for the first 2, the worker and the service, is to execute tasks, execute instructions. Whereas the last 5, the primary use of it is to store data and to store data. You're going to see some storage units in task types. You're going to see some task units in storage types. And you will talk about that in a little bit. But just have this concept that's why we have this, this differentiation. And you notice that in the icon, tasks are denoted with icons that are blue, and then storage are denoted as icons as red. These icons are going to be what we use in the case studies when we're really diagramming out what a system design is. You'll see these icons there so you can recognize that, like, oh, a square is a service, and so on and so forth, to make it easy for you to understand. Now we're going to go through all 7 of these and what they are, the trade-offs right now. So I'm just going to jump right into it. We're going to jump into it in order with the task building blocks first. So I'm going to start with the worker, and I have this trapezoid to represent it. Now I have my amazing drawing skills, like I know I have fabulous drawing skills, to try to give you some sort of intuitive understanding of what's going on here. So it's really simple. It's built with a single task unit. You have some external thing that says, hey, you need to execute this function. And over here, f of x meaning a function in math and mathematics and things of that nature, it executes a function. Now you might just say, okay, duh, that makes sense. I'm like, yes, but hear me out here. The concept here with the worker is that workers have a set of instructions, usually in a function, and that some external thing says, okay, you need to go and do it. Think of it as like a running script. Think of it as a running script or a scheduled job, things of this concept. This worker is working in the background. It's not affecting anything with the user experience. The goal, though, is that a lot of times you need something working in the background to do some necessary work to prepare for something in the future. So I have this what is it part, and I'll read it. It's, workers operate independently of a user's direct interaction, performing tasks like data processing or job execution in the background. Usually the user doesn't directly initiate these things. They are working in the background for a variety of reasons, and they don't affect that user experience. The strength of it, it's efficient for long tasks. If you have something very long that you need to do some processing that you have to do that the user doesn't have to, can wait and get notified later when it's done, it's great for that. You kick off a worker, it does its script. It could take an hour, take 10 hours, it'll run, and then it can do something to notify the user when it's done. However, the weakness, sometimes it's hard to debug. And the reason why it could be hard to debug is that imagine you have a number of workers happening in the background and something happens. You kind of have to find out which worker it is, where it was, how to get their logs. Of course, there are solutions for all these things, but again, there's no such thing as one building block that does it all. That doesn't exist. Everything has its strengths and weaknesses, but understanding this trade-off tells us like, ooh, for this situation, this would be better. And for this another situation, another thing will be better. So that's a worker. It's basically a pure task unit that has the ability to be triggered by some external force. We'll talk about that all throughout this lesson and in all the case studies as well. So keep that in mind. So we have this one task building block called a worker. Then we move to a service. Notice that it's a little bit more complicated, but it may look a little familiar. It's built with a dictionary storage unit and a bunch of task units. Now, in this diagram, we have this idea that you have this ability to send a path or send some request or what have you, right? And defined in the service, there's a number of different tasks or functions that are defined. And basically, and it's laid out in a dictionary way. If I put in a path 3, then since this path 3 is connected to this h of x function, then h of x is returned and executed. It's executed, and the result is returned. So if you just think about this, you might look like, this seems like some other things I've seen before. The idea with the service is that it gives you the ability to publicly, basically a remote procedure call a function that's externally defined. Like it's defined in the function and in the service what all these different tasks are, and you have the ability to pick which one you want to run, put it into parameters, and it will execute it and return it. Very important. This is very important to be able to, when you're creating systems, to be able to enable other parts of the system or even externally to be able to access your system and gain functionality. So what is it? Servers map publicly available paths to functions or task units that centralize resources and services for specific purposes, because these functions are task units. They can call other things as well. So they can somebody can go to path 2. G of X is executed. This can call a number of different services or external what have you, gain the result, and then return it back. So it's a centralizing force. So then, what is its strength? It delivers requested content efficiently. Hey, I wanted, h of X. I pass in path 3. H of X is executed, and then it returns it out. Very efficient in what it does. But its weakness is that its responsiveness drops with high load or slow tasks. If you think about it, right, you have these paths being sent in, right, and being executed. There's only going to be so many of these requests that any one service can handle. If there's so many of them at the one time, some of those things could get dropped, right? And typically in a service, there's nothing that's like saving different, requests or paths that are coming in. So they may just be dropped or be slow. Or slow tasks. If you have one task that takes a long time, then that might hog the ability for the service to handle other tasks. Now, if you're starting to see the trade-offs here between workers and services, services are really good at handling a number of different requests and delivering, executing tasks really efficiently and connecting different services together, different aspects of your system together. A worker, though, if you have a very long task that needs to be done, done, a worker would be better for that. You spin off a worker, it works. That's focused on that one task so that the service wouldn't have to be bogged down. So you see how they complement each other. And this is why, in this essential, these 7 essential building tasks, there's only 2 task primary units for that purpose. You'll see that we'll use we'll use both the worker and a service throughout all of our 15 case studies to build a variety of applications. So there you go. So that's it for the task focused or the task building blocks. So now we're going to go into storage. First, storage. Remember, these are the storage first. Storage first building blocks. So we have the key value store, right? Built with what? The dictionary storage unit. You notice that this dictionary storage unit is the same dictionary storage unit that we used in the service just previously. And notice that we're using it for the same thing, but the key value store is now just making that available as a pure storage like building block for our systems. That you put in a key, the key is connected to some data or some value, and then if you put in that key, it will return the value that's associated with. A key value store is a simple database that stores data as unique key value pairs for fast retrieval. Just know, so this is the thing. Sometimes we just want that key value store. And I'll say this has a variety of benefits, a variety of uses that you'll see throughout the 15 case studies in this. It's a very powerful building block. Its strength is that it's fast and scalable because it's simplicity. You have keys, you have values, easy to scale, easy to make sure it's very fast and efficient to get the thing that you need to. But then the weakness is limited query flexibility. Okay, it's fast retrieval, but if you needed to have some ability to connect data together or to say that, hey, if I get this one piece of data, then I want this other pieces of data along with it, it's very limited in that area. You'll see some key value stores might have be able to do some prefix searches and things of that nature, but nonetheless, it's, a key value store inherently has limited query flexibility in order to make sure that it's fast and scalable. That is the trade-off. So that's the key value store building block. Now let's move to the file store built with a tree storage unit. Now you see that there's like a file path that you've seen in Mac, Linux, PC. You have file path 1. You have files, just like you have in directories. You can imagine it being laid out as a tree, that you have the root, and then you have a file folder that has a path folder and has different files. So I sent in file path 1, we go to traverse from / to file to path to 1, and then returns 1, like whatever file that is. A file store organizes data hierarchically with using tree structures, where directories are nodes and files are leaf nodes. Okay, so the idea is that you put a number of files and it organizes in this tree storage unit, so that when you pass in a path, it can traverse the tree, and if it's not found, then it returns nothing. But if it is found, it gives you the actual file. So you have the ability to save raw data here. So the strength is that it organizes and stores data efficiently. It's very good at making, putting lots of, data in. It can organize it. You can find it through folders. Sometimes, has the ability to search through that as well. However, the weakness is that it can have slower performance due to fragmentation. If you think about it, right, at the end of the day, again, everything is zeros and ones. So when you save files, it's going to save them in a specific location wherever your hard drives or what have you that's saving it is located. This tree structure makes it efficient to find where data is, but imagine if one is saved, it was like file 1 was saved, today, and then file 3 was saved like 3 years from now. Typically, file 3 will probably be very far away memory address-wise than 1. And so therefore, sometimes that whole lookup might become slower because of over time, when things are saved and deleted, you have that fragmentation. There's things that are done to defragment and to deal with this, but there's something to consider that if I have like structured data that I want to access really fast, really quickly, a file store is probably not the way to do it. Key value store is the way to go. But if I have raw files that I want to be able to store and to be able to retrieve efficiently, this is, the file store is the way to do it. So again, even storage building blocks have their strengths and weaknesses. All right, so let's move to the queue. And this queue is interesting because this is one of like really, if you want to talk about like building real systems, this is used in so many different areas that really can provide um, not only scalability, but reliability into your system. So the idea here is that you have a trigger that says, I want the next item. And then you have like a list of items in a queue that's being put in, first out. And if I request an item, I get the first one that was put in, and it gets popped out. And then item 2 would go to be the next one. So if there's another request, I get item 2, and it's just like a queue. If you're lining up, somebody lines up, the first one who was on the line gets served first, and then the second one, and so on and so forth. This is built with an array storage unit. Have things in an array being requested and taken out in a certain specific way. So a queue is a data structure that processes items in a first in, first out FIFO order, commonly used for tasks like scheduling and buffering. You're going to see this a lot too, that all of a sudden you might have two systems and you've put a queue in it. All of a sudden it decouples them because one can put their request in a queue, the other one can retrieve it, and all of a sudden if one is down, the other one doesn't fail, and so on and so forth. We'll talk more about that later in the case studies. But one to note that this is a key building block to be able to store future tasks to be executed, store future like data to be processed. There's a number of uses for queues that you'll see. So the strength of it ensures fair and orderly processing of tasks. You can have several different services doing a bunch of stuff, sending things in a queue. In the queue, whoever puts it in first will have it in that order. And then the people, and you pair this with a worker that can maybe take an item and do something with it. All the worker knows is like, oh, I'm going to get the next one. I'm going to get the next one. It doesn't matter how chaotic all these items got into the queue because the queue makes them ordered. Now, the weakness, though, that it can become a bottleneck if items are added faster than they are processed. If you have 7 services putting stuff in the queue and only one worker putting it out, it may just get larger and larger and larger, and that can end up being a problem. So again, even the queue has their strengths and weaknesses. Now we're going to go into a little bit more complicated storage building blocks. You have the relational database built with a task unit, an array, and tree storage units. I'm going to first read the definition here. A relational database organizes and stores data in structured tables with rows and columns, enabling relationships between tables through keys for efficient query and management. Now, this is what's happening. You've seen, if you use spreadsheets and so on and so forth, you understand the row, you're going to have a table that has rows and columns and understand things. So a relational database has a number of these tables, but however, there's a lot of cases where these different tables have relationships. Like you'll see in one of our case studies where, let's say the blogging application, you may have a blog post. Blog post can be a table that has like the information of it, but then you might have comments. And then there could be 5 comments that are associated with one blog post. How do you make that link to it? And how do you have something to make sure that these links are proper, that like I can assure that each comment, there's no such thing as a comment that exists by itself. Each comment has to be associated with some blog post. How do you do that? Now, a relational database handles these sorts of relationships. It provides the ability to have structured data and to be able to structure the links between the tables and make sure that that happens. So that's why you have the task unit over these array and tree storage units. There's 2 of these arrays to represent the tables, the tree storage units that provide the links between the tables, but you have it all surrounded by a task unit that takes in instructions on what information to get, what information to insert, to delete, to update, things of that nature. And then it operates, it does operations on these arrays and tree storage units to give you the data result. We've been using relational database for decades now. This technology is very robust and mature, and so that's why it is a key, a fundamental building block in our systems. So again, though, everything has a strength and weaknesses. The strength is that it ensures data is correct and available. If you can be assured that if you put in an instruction in there and this data result comes out, it's correct. That is what its strength is it has lots of checks and constraints to make sure that that happens. However, because of all that additional overhead to do so, massive scale is difficult. It is hard, not impossible though, but it's hard to scale this out very to to a very large side and also still guarantee all of this correctness and availability of the database. So you have this trade-off. So you'll see a number of things that there are a number of things that would say, hey, let's use this simpler storage unit for certain things so that people don't have to always go to the relational database to get data. You'll see things like that a lot. So that's something to keep in mind. So now we're at the vector database, our final building block. You'll notice that there's a lot of similarities between this and the relational database. It's made with a task unit, an array and tree storage units. And you'll see that you put in instructions here and out comes a data result. And you'll note that there's links to the, to the tables or to the arrays, I should say. But the data is interesting. I made them blank before because like for relational databases, because that's data that's inputted by us, by humans. These are all numbers. They're vector databases are filled with vectors, and mathematical vectors are filled with numbers. A vector database stores and searches data as mathematical vectors, often used for finding similar items in application like AI and recommendations. The key thing here is that what a vector database does is that it takes data from from file stores, from relational database, and so on and so forth, and it's converted into vectors, into numbers essentially, and are saved into a database in a specific way in these higher dimensional matrices, essentially, that are connected to each other. That's what the links are for. What this is used for is to be able to find similar items and applications like AI and recommendations. Think about that, like when you interface with, let's say, a chatbot, and you're able to say like, hey, I give you this data, please summarize it. Can you give me a synonym of this? Can you understand what this text means and things of that nature? How is it doing it? Listen, I am not a machine learning engineer. However, again, especially with like the engineer we're trying to do, it's very important to understand, at least to some level, all the different aspects of the system that you interface with. The idea here is that if you take data and convert it into these vectors, and if you're able to take another, a query and convert that into these numbers as well, you can be able to find, it's like, hey, listen, I'm going to search for this vector. What is nearby this vector in this, multi-dimensional space that's inside this vector database? That's how you can find like, synonyms of words or summarizations of items, because there's so much data in here that you have this ability to search what's nearby in a mathematical sense. So the operations here are mathematical in nature, but inherently, by finding out what's close by it and be able to convert that back into information that we understand, like with English or like English for my language, or language I should say in general, or images or video, whatever that is translated, or like information for another system to pick up, then we have this ability to find out what's similar in this semantic way that we couldn't have done it anywhere else. Like this takes like regular expressions and rule-based search to a level that we've never seen before. So that there's to the point where sometimes we might not even fully understand how it knows what's like, why this is near another point, but we do understand when we look at the translation that yes, this is pretty similar. And so it's a very powerful way that's powering these AI applications that's enable us to do things and understanding to a level that we haven't had before. So it's a very powerful database that's been used earlier, but it's just now this is becoming more known of as an aspect, as a building block of what we use, to build systems, and that's why it's our final building block here. So again, everything has its strengths and weaknesses. So it's good to understand, even though we may not know all of the advanced mathematical equations and stuff like that that's happening here, we can understand strengths and weaknesses just like with relational databases. So The strength is that it, again, excels at finding similar items quickly in large data sets. It can, if you have a big data set, it's like, oh, what are similar to each other? Find it very quickly, and then that able to be returned and used as used for in the rest of the system. But the weakness is it's less precise and scalable for very large data sets or exact matches. So there is a scalability aspect here. There's a processing aspect to have that task unit process large amounts of data. Also, it's very good at similar, but it's not that great on exact matches. But again, this is how there's trade-offs between one thing to the other. If you really want to have exact information, a relational database has all of the mechanisms to make sure that what your data is put in is what you get out. If you want similar items, this is where vector databases shine. So again, even with this aspect, there's trade-offs between different storage units, storage building blocks that you can use. All right, and that's the 7. We also want to, I'm introducing these external entities here because when we have case studies, we're designing a real system. So there's certain aspects that we need to add into it to show how things interact with other, external forces, and so on and so forth. So there are just three external entities in addition to the 7 building blocks that you'll see in the 15 case studies. First, there's a user that have a nice little smiley face representing the end user that's interacting with the system. Sometimes there might be more than one user, but we want to represent that hey, this is when a person's interacting with the system. Now we have a concept called time, represents a scheduled and or recurring external trigger. So you have this idea that hey, in 15 minutes, this should execute, or this should happen in 2 months from now. We represent that aspect as this hourglass looking icon. And then we have an external service, represents an integration to a service that's outside the system. The idea is that most systems don't do everything that it needs to do. Sometimes, especially if some attributes require very specialized understanding and knowledge, that sometimes you do build a system and then you integrate with something externally. We want to add that aspect to these system designs to understand and show how we do that in a building block principled way. That's why you have a little cloud icon for that. So you'll see these 3, these are not, I call them external entities. These are not building blocks. These are things to represent how the system we built interfaces with users, interfaces with specific things that have to happen at particular time intervals, and external systems that it integrates with as well. And that's it. So you are now ready to jump into our 15 case studies. But before you go, here are 3 key tips before you jump to the next section. First tip, we will build all 15 case studies using these 7 building blocks only. External entities are used solely as necessary. If you don't fully understand any building block, return to the fundamentals of practical design section, this section, as most building blocks will be repeated frequently throughout the 15 case studies. You don't want to kind of keep going off if you don't fully understand, what is that vector database going in? Come back and make sure that you understand that. You understand the tree, the task and storage units and the different data structures and things of that nature. Make sure you understand that. If you're a little bit confused, go back to that section, listen to that, seek some external sources as well before you move on, because it's just really important to understand the role that each building block play. Second tip, please go through the case studies in order from 1, 2, 3, so on and so forth. Later case studies refer to previous case studies to build your senior level intuition so that your mind makes the necessary connections. Like in case study 3, I will refer to case study 1 and so on and so forth. So please do it in order so that you can kind of see the progression of just I introduced this, and this building block was used in the same way in these other items. So even though you could listen to them ad hoc, it is done in a way that to build that intuition, to listen to them in order. The third tip, in these case studies, you will often see 2 building blocks connected as a single entity. Note how their combinations can serve different purposes and functionalities. Understanding these connections is key to developing senior level intuition and recognizing how the same combinations can be applied in various ways while following the same principles. So, for example, you'll see this block with a diamond, a square representing a service connected to a key value store. You'll see this combination used as a cache service, as a cache, and we'll talk about more about that in the later case studies. But you also will see the same symbols used as an authentication service. And I'll talk about why these two combination of building blocks serve those two purposes. And then you start to see that, oh goodness, this service connected to a key value store can serve a number of different purposes because it combines the availability that services provide versus and the fast storage, the fast retrieval of storage that key value stores have. The combination of these two enables that two combination to have a number of different very useful purposes in a number of different applications. And that's it. I'm excited to see you in the next section. This was from my original course on system design for junior engineers. Since then, I've refined and expanded everything you just saw into the full system thinking the AI era course, using these same building block principles across 15 plus real case studies. If this resonated with you, the link is in the description.